All right, we're going to do our final topic for this unit and this course, which is still dealing with sound, but we're going to look at sort of a weird sound phenomenon that we call the Doppler Effect. What that is we hear a different frequency than what's actually creating the sound due to movement. So a good example would be you watch a race car, whether you're watching live or on TV, you hear the car go by, you hear the kind of sound. So the pitch or the frequency of the sound seems to be changing as the car is coming towards you or away from you. So what we got to remember is the true frequency doesn't change, because that's what's creating that noise, whether it's the motor or a siren, the pitch of the siren, or whatever we're talking about. It's that movement that makes it appear differently. So what's happening here, if we kind of look at this little diagram, kind of a bug on water. So if the bug was just staying in the same spot, bouncing up and down, we would get our sound waves just making that normal circular pattern. But what's happening now is the bug is making the wave, but it's also moving to the right. So you can see, so the new wave is centered around him, but the old wave is still in the previous location. And as he keeps doing that more and more, keep moving to the right, you can see we get this sort of compressed sound wave. So you can see on this side, to the right side, our wavelength is a lot smaller than it is over on this side. So we got a further wavelength. And because our speed of sound isn't going to change due to the air or whatever it's in, we get a smaller wavelength, which is going to make a higher frequency. And then on the back side, we have a bigger wavelength, which is going to make a lower frequency. So if the car is coming towards you in a race car, you hear a higher pitch, and then as it goes away, you hear that lower pitch. So I'll make the noise again, but you'll hear as from start to finish, you can hear the pitch goes down. It goes. So as it's coming towards you, it's higher and higher, and as it goes past you, it gets lower and lower. So that's basically it. If the object is moving towards you, you hear a higher frequency. Away from you, you hear a lower frequency. So the formula we use to actually calculate this has a few parts to it. We have velocity of sound in air, whatever we're talking about. So that usually is given to us, and that's usually our 343 or thereabouts. But then we have the velocity of the source, whatever's making the noise. So if it's, let's suppose it's a car or something going by at 30 meters per second, you can see we either add or subtract that 30 meters per second to our speed of sound. And then we multiply all of that. So that's just a ratio. That whole velocity thing is just sort of calculating the ratio of the speed and how it's going to change. We time that by the actual frequency of the source. And then what that's going to actually calculate then is our apparent frequency. So a couple of key things you got to remember is if you're stationary, so you're watching a race car go by and this car is coming at you at 30 meters per second, it's coming towards us. Remember, that's going to make a higher pitch. So to get a higher pitch, we actually need the bottom number of the fraction to be a smaller number. So the higher pitch is actually the negative. So if it's coming towards you, we need the minus. So in this case, we'd have 343 divided by 343 minus the 30. Okay, so the easiest way to remember this is if the distance gets closer, you're making the gap smaller and smaller, we use minus. If the distance is getting bigger, it's moving far away, then we would use plus. So if the car is over here and it's going away from you at, let's say, 25 instead, we would use the plus. You'd have 343 over 343 plus 25. And that's really it. So there's nothing too complicated. So let's go through a couple examples. So it says siren of 8,500 hertz. It's got a speed of 300, and it says the ambulance is approaching you at 25. So our formula, we would use our velocity, which is 300, divided by 300, and we either add or subtract the 25 now. So if it's coming towards you, our distance is getting smaller, so we want to use minus. We times that by 8,500, and then for part B, we basically do the exact same thing because it's now moving away from us, so we use the plus. So we just do those two calculations, and you see they're similar answers, but not quite the same. So 300 divided by 300 minus 25, times that by 8,500. So we should get a higher frequency because it's moving towards us. So we get 9273 approximately. And if we do the second one, 300 divided by 325 times 8,500, that one's moving away from us, so we should get a lower frequency, which we do. It's 7846. Okay, so pretty easy calculations. The only thing you want to be careful of is if you're both moving. So I don't have an example on that one, but let's suppose we're in a car, let's suppose we're moving at 30 meters per second this way, and then we have our ambulance coming towards us at 25. So we're both moving, so we're still moving the distance smaller and smaller, and it'd be the exact same thing as if we were standing still and the ambulance was coming towards us at 55. So you just got to be careful of directions. So in this case, we'd have 300 divided by 300 minus 55. So we add our two speeds together, but it's getting closer, so we subtract. Let's look at sort of the opposite. If we're going 30 one way and the siren's going 25 the other way, together they're moving apart at 55, so we go 300 over 300 plus 55. So together and apart, that part still works the same. And the only other one that's kind of weird is if, let's suppose you're moving 30 and the siren or the other object is at 25 and you're going towards each other, like you're going in the same direction. So you can see our behind one is closing the gap at 5. So in that case, you just do 300 over 300 minus 5. And if it was the other way around, if the 30 is in front, it's going to get further and further away at 5. So it'd be 300 over 300 plus 5. So those kind of things are a little bit weird, but just use some common sense and put the speeds together if they're going towards each other, put them apart as a plus if they're going away from each other, and that's it. So the last thing we'll talk about quickly is what happens if you actually go faster than the speed of sound. So we saw, let's go back to that diagram where we had our little circles. So this is where you're going slower than the speed of sound and you're moving, but we could actually create the scenario where the object is actually in front of the sound waves, right? It goes fast enough that it passes the sound waves. So what actually happens in this case is we get this compression. If it's right at the speed of sound, all of these waves are basically all together. So we get this compression of air, which actually acts like a wall. It's almost like a wall of compressed air. So it's pretty hard to break through it. But if you do, you end up getting the object out in front, and then all the sound waves are behind. And we get these sort of like weird cone-shaped sort of patterns that come from it. And that's when we break the speed of sound. So a jet airplane or something can actually do that. And but once they break through, they sort of get in front of the air. So if you're an airplane breaking the speed of sound, you can see in this little picture in the video, you can see it sort of makes that little cone shape. The moisture in the clouds follow the compression, so you can see sort of that cone shape where it's breaking through that speed of sound. So if an airplane was to fly by faster than the speed of sound, as it's going over top of you, you wouldn't hear anything. But as soon as the sound catches up, we get this basically loud crack or this loud boom where that compression basically comes towards us. And I've got this other kind of cool video showing they're speeding up a ping pong ball to go faster than the speed of sound, and you can see the effects of that one. So check out those videos, and speed of sound and breaking the speed of sound is just more of an interesting thing, but it does indeed happen. So if you crack a whip, you just whip a whip, that little tip of the whip that makes the snap sound, that's the reason it makes that noise is because it's breaking the speed of sound, so we get that little crack at the end. So that's another good example. Okay, that's it for this topic.